All right, let's talk about one of the most powerful tools in all of science, the periodic table. And trust me, it is so much more than just a boring chart you had to memorize in school. Think of it like a treasure map, a cheat sheet to the building blocks of the entire universe. I mean, seriously, think about that for a second. How would you even begin to organize everything? All the stuff that makes up you, me, the stars, everything. Well, chemists came up with an absolutely brilliant answer. One master document to sort it all. And that is the periodic table. So here's how we're going to crack this code together. First, we'll get the lay of the land, the big picture. Then we'll dive into the different neighborhoods, the element families. After that, I'll show you how to read any element's personal ID card. And finally, we'll see why the whole layout is just pure genius. Okay, let's start with the basics. The absolute best way to think about the periodic table is like a giant city map. Every single element has its own specific address, and that address tells you pretty much everything you need to know about who it is and how it's going to act. Now, the first thing you'll probably notice about this map is that it's broken up into three main territories. You've got this huge chunk on the left and in the middle, that's the vast kingdom of the metals. Then tucked away in the upper right corner is the much smaller neighborhood of nonmetals. And right on the border between them, you have this tiny little strip of metalloids. So these regions aren't just some random coloring on the map. Oh no, they're defined by completely different, almost polar opposite behaviors. And this, right here, is where the real story of the elements truly begins. Okay, so on one side, you've got your metals. Think of them as the ultimate givers in the universe. They love to get rid of electrons, which makes them great at conducting electricity and leaves them with a positive charge. And on the complete other side, you have the nonmetals. They are the takers. They are desperate to grab more electrons, which makes them fantastic insulators and leaves them with a negative charge. And straddling that line right between the givers and the takers, those are the metalloids. You know these guys, silicon, germanium, they're the heart and soul of all our computer chips. See, they're not amazing conductors like metals, but they're not total insulators like nonmetals either. They're semiconductors, landing perfectly in between. All right, let's zoom in even closer. If the whole table is a map, then the vertical columns, the groups, are kind of like families. And everybody living in the same column shares one crucial family trait, the number of electrons they have in their outermost shell. We call those valence electrons. And that one number, it basically dictates their entire personality. So first up, let's meet the life of the party over in Group 1, the alkali metals. These are the most reactive metals on the entire table. I mean, they are so desperate to give away their one and only valence electron that if you drop them in water, they literally explode. They're not called the explosive extroverts for nothing. And this is the key right here. Because elements like lithium and sodium have just that one single valence electron, they will do anything to get rid of it. And when they do, they form a positive one ion. That one little fact defines their entire super reactive chemical life. Now let's jump all the way across the map to group 17. This is the home of the halogens. And if the alkali metals are the generous givers, well, the halogens are the ultimate takers. They are just one electron short of having a full set, which makes them the most reactive nonmetals, always ready to steal an electron from anyone they bump into. You see the pattern here? Elements like fluorine and chlorine have 7 valence electrons, so they aggressively hunt down one more electron to feel stable, and that gives them a -1 charge. They are the chemical polar opposite of the alkali metals. And finally, way over on the far right edge of the table, in group 18, we find the cool, kinda aloof noble gases. These are the aristocrats. Why? Because they already have a full set of 8 valence electrons, which is like the magic number for stability in chemistry. They are perfectly content. They don't need to react with anybody. So that full outer shell makes them chemically inert. You know, neon, argon, they're the happy homebodies of the periodic table. They've already reached chemical perfection, so they just keep to themselves. They're happy as they are. Okay, so we know the neighborhoods and the families. Let's zoom right in on a single square on our map. Each little box is like an element's ID card, and it's packed with all its vital statistics. And you know what? It's actually super simple to read. Now, the most important number in that whole box is the atomic number. This number is, well, it's everything. It's the number of protons in that atom's core, and it defines the element's fundamental, unchangeable identity. Gold is gold because it has 79 protons. That's it. End of story. And with just the numbers on that ID card, you can figure out the entire recipe for any atom. It's so easy. The number of protons? That's just the atomic number. To get the neutrons, you take the bigger number, the atomic mass, and subtract the atomic number. And for a neutral atom, one with no charge, the number of electrons is exactly the same as the number of protons. Simple as that. But what about ions? You know, atoms that do have a charge. Well, let's take a look at aluminum. Its atomic number is 13, so it always has 13 protons, no matter what. As a neutral atom, it also has 13 electrons. But to become more stable, aluminum, being a metal, gives away 3 of those electrons. It still has its 13 protons, but now it only has 10 electrons. That imbalance gives it an overall charge of +3. Okay, let's pull the camera back out for a second, because this table isn't just a catalog of all the elements. The real genius of the periodic table is its incredible, almost spooky power of prediction. The secret is all in the layout. Because of how everything is structured, you can spot trends just by looking at it. We know, just by its position, that an alkali metal from group 1 is going to be way more reactive than its neighbor in group 2, the alkaline earth metals. And those, in turn, are more reactive than the transition metals. The map just tells you the story. And that, right there, is the magic of the periodic table. An element's location, its address on this beautiful map, tells you almost everything you could possibly want to know about how it's going to act. Is it a giver or a taker? Is it going to be explosively reactive or totally chill? The answer is right there in its position. And here's the wildest part. This incredible map isn't even finished. Right now, in labs around the world, scientists are still creating new super heavy elements, literally pushing the boundaries of what can exist and adding new addresses to the very end of the table. And that leaves us with one final fascinating thought. What new properties, what new personalities are we going to discover next? What will the next element we add to this incredible family be like?